Okay, tonight we're privileged to have three guys from Caterpillar Generators to talk about CHP and resiliency of power. They have a massive wealth of personal and business experience to do with generators, and it sort of seems to be a hot topic now at the moment with resiliency of power and also using green energy friendly sources for power, backup power. We've seen in Texas where, it's not, because of changeable weather conditions now, we're not always going to be in a place where we can rely on the utility all the time. And the current market is to try and get as much, if you've got energy that you can use in the form of CHP that you're now not using, then you can be looking at using waste gases or waste heat. Waste gases really, and using CHP to generate electricity. Obviously, it's not a one solution fits all, but hopefully we'll have a bit more clarification about matters like that in the talk. So thank you very much, guys. No, we really appreciate you making the effort to present to us. Thank you.
Thanks, Richard. Pleasure to be here. We don't get to talk to many people these days, so. But anyway, my name is Jim Boyd, Project Development Manager for Finning Power Systems, and I focus primarily on oil and gas, specializing in lean burn power generation for the last 9 years. So basically looking at any application you can put a gas genset into. Couple of colleagues along tonight is Sid Kuzmanovic in Edmonton and Chris Shermans in Vancouver. We heard a bit from both of them later tonight, and they can introduce themselves then. For the next 40 minutes, we'll be touching on the role of gas gensets and adding resiliency to the grid, enabling the use of renewables and microgrids. We're not going to go into too deep, but if something does grab your attention, we can follow up and dig deeper as you guys need. So, before we dive into CHP, I'd like to touch quickly on Finning, Finning Power System, in case you don't know who we are. I know there's some oil and gas experience on the line, so should be familiar with us, but just in case. We are the biggest Caterpillar dealer in the world, founded in 1933 and headquartered in Vancouver. As you can see, we're 5 decades of global experience putting power into Western Canada. Lots of experience in mining. As you can see, other challenging installations, Arctic and high elevations. So for modular power plants, alternative fuels, custom controls, complex systems, we've got the capability to execute across any industry and application. We've got access to factory engineered solutions, or can design and build to order in-house. In short, there's nobody better qualified to put a CAT into the operation across Western Canada or into a subarctic environment in Finning. That's the end of my Finning sales pitch for tonight. So first of all, I'd like to touch on resiliency. As Richard did say, Texas was a bit of a big event, but extreme weather events, they account for over 70% of power disruption across North America. As you can see from this map, 2018 alone, there were 14 separate billion-dollar weather events that impacted the US. Texas we touched on, but the thing that started that off was Katrina. Katrina was a complete game changer for gas gensets. If we maybe look a bit closer to home, the flood. So what we saw back then was these diesel gensets in perfectly good working condition that simply ran out of fuel. So with all the climatic events, power disruption, Caterpillar's invested very heavily over the last few years at developing gas gensets up to 2.5 megawatts that can meet the requirements for NFPA 110, and that's for fast start times and load acceptance. There's nothing else like them on the market. Anyone with experience in natural gas power generation, they know there are some pros and cons. But being connected to an infinite fuel source and the fuel security that brings, it does make a powerful case to replace diesels with nat gas standby gen sets. Now, if you couple that with installing CHP locally, you could build in the capability to potentially disconnect from the grid at times of high demand, or even just maintain power should a power outage occur. There was a critical infrastructure project that was slated to go into Edmonton. Would have had a gas standby genset and full CHP system, but unfortunately, that one get cancelled. Change of government and the plug was pulled on the funding, but we're hoping it comes back. I mean, on the renewable aspect, I'm not sure if you guys keep an eye on the AUC applications. I get notifications every other day. But there has been a marked increase in renewable applications over the last few years with wind, solar, battery storage. But as we know, renewables are the substitute for conventional power generation. If the sun doesn't shine or the wind doesn't blow, you still need to back those intermittent renewable energy sources with conventional, just to ensure that you don't sacrifice grid stability. The CHP can help take the strain off the grid, and with the recips being able to come online quickly, that can help us respond and recover quickly, more importantly. It has been demonstrated that CHP installations can help facilities ride through power outages, as well as delivering the typical return on investment that things were initially designed for. So if we turn specifically to CHP, the benefits are the same as they always have been. The big change that I've seen is the language you hear when you talk about it these days. I mean, the current buzzwords of decarbonization, emissions reduction, resilience, and decentralized power generation. They kind of shifted the focus around the application. I mean, in the past, CHP was all about offsetting utility costs, but if you had a reasonable spark spread, the decision whether to go ahead with the project is typically based on return on investment alone. But with changing market conditions, green initiatives, upcoming carbon tax expected to reach $170 a ton, it's not only the base price that's paid for electricity and gas that are making heat recovery attractive in the West. Companies are looking really hard at how they're perceived in the market, and they're taking steps to reduce their carbon footprint. It's really starting to make sense in Alberta. I mean, we've had historically low gas and power prices, and CHP has typically been a stretch for the West, pretty much for those reasons. But I mean, outside of, to Richard's point, wastewater treatment plants and landfills, we have seen those. But if you look towards the east, towards Ontario, those market conditions are coming west, without a doubt. They invested heavily and also protected the revenue of those who were generated using renewables at a fixed over the market price. The coal phase out started in 2005. The Green Energy Act came into effect in 2009. The big thing that was seen was the power prices impacted the industrial sector massively. Power prices were 3 times higher than you would see in Calgary, and the net result was 75,000 job losses and a market badly in need of creative solutions to cut costs. So anyway, I really do believe that's where we're going. But I mean, CHP itself, it's not a new technology. I mean, 1882 at Thomas Edison's Pearl Street Station, the world's first commercial power plant, was a CHP installation, generated power and also provided heat to the neighboring buildings. So from microsystems to large industrial installations, it's never made more sense than it does today. We can provide hot water, steam, um, chilled water or sorts of chillers, or all three at the same time. The main thing is it all comes down to making the most of the fuel that we burn today, getting the best bang for your buck, carbon footprint, all of the above. So if we take a look at large centralized power plants, traditional power generation, what you're typically going to see is well, more than 62%. I'll take it the other way. 62% on average wasted by generation transmission. So what you're going to see is 38% delivered to the user. Now I got this one from Caterpillar. I did see another one fairly recently that showed the average US efficiency with a coal generating plant at 30%. Again, just food for thought. If you consider installing localized generated by power displaced boilers, you can achieve much higher efficiency. If you take a look at this one, your average cost of 60% genset there. That's showing 90%, and that's if you're chasing all the sources of heat off that genset. And where typical achievable number is likely 80%. So let's see. So if you're generating power and heat from two sources, obviously your emissions are up. If you can produce power and heat from one source, it's obviously cleaner, using less fuel, lower emissions, and all in a smaller smaller footprint. So sources of heat. So what can we tap into? So today's high efficiency gen sets can typically hit around 43 to 46% electrically. So if we chase everything, yes, we can achieve over 90%. But typically the low temperature circuit on the engine is dumped because it's low grade heat. I'll touch on that in a second, but the high grade heat, the easy stuff to chase is jack and water and exhaust. And that's going to make up a big chunk of that 43%. Sorry, excuse me. So the low temperature side is usually dumped because of the low temperatures associated with it, unless you have a process for it, or maybe use that low temperature as a preheat for the process side. It is typically dumped. A lot of that depends on the approach temperature on the process side from the plant. So across, I'll just touch on exhaust waste heat. You may notice that exhaust waste heat to 120 degrees C, that temperature does vary across applications and components that you're expecting to see in the exhaust stream. Basically, if you extract too much heat, we can condense. That means you're then pushed to using stainless steel equipment. And you also have to deal with the water that you actually produce at that point. If there's anything nasty in the fuel, such as H2S, LOX stains, that can also lead to acid production, cause damage with the genset and the heat recovery equipment attached to it. So clean fuel on this type of thing is a must. That extra 5 to 8% at the bottom, that's specific to greenhouses. And I will touch on that a little bit later. Would like to move on and look at hot water generation first. So hot water is the most common application we see for heat recovery on a recip. See from this example, we are in fact dumping low temperature heat. That's this circuit. Can everybody see my arrow, by the way? Somebody nod.
Yes, we can.
That's it. Yeah, so, but if we follow the flow of this thing, this is the jacket water heat leaving the engine after the thermostats crack open at 95 degrees C, goes through the plate and frame heat exchanger, and then back to the engine at 85 degrees C. So that plate and frame is this thing. It's fairly small, compact, but actually really very efficient. So again, we follow the flow. From the customer side, this is the process side. So coming in, heat transfer through the plate and frame heat exchanger. And then we go up to the exhaust gas heat exchanger. And that is this bit of kit on the right. The flow from the water is typically against the exhaust flow. And then we take this side back to the customer, back to the plant. So if you look at the exhaust gas heat exchanger, you will see that piece is a bypass damper. So if we did want to run the genset in power only, we can close this damper. We can bypass this bit as it takes place, and the exhaust flow will go that way, straight to the exhaust stack and not touching the heat recovery part. And see from here, cold water in, comes along the tubes, and hot water back to the plant. And again, exhaust flow goes against the fluid flow. Okay, we want the steam. The layout for steam, it is similar, but as this is giving steam and hot water to the plant, so same thing, coming out of the jacket water heat exchanger back to the engine, from the process side and back. So what we're seeing is again 500 degrees C exhaust gas going through the boiler. So this thread accumulates steam at a pressure of between 8 and 15 bar, and that's 115 to 215 psi. So there are a few more safety considerations when we look at steam, but the concept is still fairly basic. I know good mechanical engineers that are probably falling asleep by now, but the process is very, very simple. But a recip can really only generate. Chris, just let me know I'm getting a lag in the video, so I hope my connection holds. Recip engine can only really generate low-grade steam because of the relatively low temperatures. And if you need high-grade steam, turbines are probably a better option. And in most cases, the case to go with a recip or a turbine, it really depends on what the customer needs. But if the bias is towards electrical, gensets are a lot more efficient than turbines beneath 20 megawatts. Something to consider. Moving on to absorption chillers. Haven't really dealt a whole lot with them, but again, the concept is pretty basic. Used to chill the jacket water and the exhaust stream, using both. It provides cooling through the process of evaporation and condensing of typically ammonia or lithium bromide. That cools the water going through the chiller. I see the example of this one is very similar to the hot water one of the previous slides, with the exception that this concept is very similar. Greenhouses. I think we're going to see more of this. It is the most technically challenging system that we deal with. We can use, obviously, you can't simply pump exhaust gases into a greenhouse because number one, you're going to poison the crop, but number two, you're going to cook the crop. So we'll maybe just touch on the exhaust gas treatment first. So what you need to deal with is the NOx, nitrous oxide, carbon monoxide. This has to be done before the heat recovery, as the heat is necessary to for the chemical reaction to drop out the toxins, if you like. So let's see. So the SCR shown that involves urea injection, and that takes care of the NOx part. And the catalyst blocks. The oxycat that you can see there is to the carbon monoxide. The heat recovery itself, that's typically done in two stages, with the second one being a condensing exchanger, because we're dropping the exhaust gas temperature to the point where condensation is formed. That's typically collected in a hot water tank and can be used for heat as needed by the plant. And after the exhaust gas is created cool, it's pumped into the greenhouse. And in many applications back in Europe, that excess power is usually put back on the grid as an additional revenue stream. I think that does look very busy. So if anybody wants to talk about greenhouses after this, please let me know. Last one, electric power only. Bypass the heat recovery side to let these things produce power only. So yeah, this slide just illustrates a general power generation application, but it is pretty common to have this an option on a CHP application. At this point, I'm going to hand over to my colleague Sid.
Thanks, Jim. I'm just going to pick the right file here to share. And let me put it in the presentation mode. Is this working? You guys see the presentation mode correctly?
Yes, yeah.
All right, great. And you guys can hear me well?
Yes.
Yeah, I can hear you loud and clear. Everything's good.
Oh, good, good. Okay, thanks everybody. Thanks, Jim. As Jim said, my name is Sid Kuzmanovic. I'm also a project development manager here with Finning Canada. I been in power generation industry for about 20 years, and Richard and I met long time ago. I think when Richard was in Edmonton, I started really in emergency power installation, you know, utilizing transfer switches with diesel and natural gas generator sets. And for about last 2 years, I've been working and concentrating on gas to grid type of applications. So where Jim left over, I guess to add up to some of the CHP examples here for us. And let me just, I kind of looking here between a couple of screens, but okay, on this particular slide, we have, you know, our combined heat and power site at Edmonton International Airport. We have installed electrical capacity of 4.5 megawatts. Engineering design was led by Finning, focusing on strict Caterpillar guidelines and commissioning checklists, as it says right there. This site is consisting of 3 high electrical efficiency Caterpillar G3512H generator sets, each having 1.5 megawatt electrical output. As you can see, each unit, these are the units as they're getting packaged on the right, and on the left are units on site. So as you can see, each generator set has its own enclosure. These enclosures are very spacious to allow ample space for preventive maintenance and scheduled overhauls. These generator sets have to be touched on a regular basis, you know, between oil changes, spark plugs, and as we said, some scheduled top end overhauls and bottom end overhauls. So this might be important for the site. You know, some sites might just say, oh, I'm putting it inside, I don't need enclosures. Some sites might say, you know, we're putting it outside as well, just like this, let's put them in the enclosures, right? So these enclosures are sound attenuated. They have heat dump radiators also. So what Jim was saying, in case you want to run in electrical mode only, or in case you're running in summer months and you don't require the heat, you have a heat dump radiator, in this case, right on rooftops. Next to them on the rooftop is also a heat exchanger. The jacket water heat exchanger is inside of these enclosures right in front of the engine. And as Jim pointed out, it's not very large. They're surprisingly small for what they do. This site Finning engineered and built custom controls for paralleling and heat recovery operation. And these Caterpillar generator sets run in parallel and supply heat and power to Edmonton International Airport. So right now, there are government incentives available through Emission Reduction Alberta. I'm not sure if you guys are familiar or seen this. They have a website. So we successfully registered on the website as a eligible contractor. Even though we're a manufacturer, supplier, and we could be a contractor, I think the prerequisite said if you're one of those, you just register as a contractor no matter what. So the website is www.eralberta.ca. It says right on here, basically you can end up with incentives up to $250,000 per project, but it's roughly about $500 per kilowatt. And it's strictly on first come, first serve basis, you know, so there's a allocation of money, and apparently when it's gone, it's gone. But I mean, who knows what's going to happen, you know, as this kind of goes on and evolves. When it comes to CHP, what kind of things you require for information? As you can see here, we put a couple things down in order to decide on technical feasibility of the project. We need certain site information as well as information found on the generator set data sheet. So from the site information, we need to know electrical load profile to understand the loads present and size the genset, thermal load profile to understand what the site will be using the heat for, the media used to transfer the heat. It can be steam, water, or oil, depending on the need. This will definitely affect the design of heat exchanging equipment. And of course, we need to know the temperature of the site media into the heat exchanger and desired output temperatures. From the generator set data sheet, we can obtain genset kilowatt ratings stating the electrical output, thermal energy from each heat source, you know, coolant and exhaust, heat source, flow rate temperatures, and so on. So this is some of the basic information needed to select the genset and choose the appropriate heat source. Additional information will probably be needed from the site to properly do a complete feasibility study. It's obviously a lot more to the feasibility study than we'll have a chance of showing here right now tonight. But site electrical and thermal requirements, the main requirements for CHP project are sufficient and electrical thermal loads, base electrical loads. So a steady state constant load is required to justify the genset selection, and sufficient thermal loads are needed in order to properly utilize the heat source from the engine. The optimum system has thermal and electrical load balanced, as the available heat energy is dependent on the electrical output. Basically what it's saying, based on how much we load the engine is how much heat we're gonna have. If thermal energy use is high, then the electricity must be utilized elsewhere or sold into the utility grid, or the system size must be reduced and all thermal loads cannot be supplied. So what this means is that maybe we would need a supplemental boiler for our high heat demand months. If the electrical energy use is high, then the excess thermal load must be dumped, thus reducing overall efficiency. So what Jim is saying, we can run in electric mode only with the radiators, on the roof or somewhere else, and we solve that way. Today, people in Alberta find way for that financially to make sense as well. They just want to run generator sets, make electricity. They, because the source that could need heat is maybe far away, and gas where they want to generate is available and cheap. So Caterpillar has this CHP calculator, and Jim and I were looking at this yesterday and today and trying to figure out what numbers to put here for this presentation, because it's actually a little bit more complicated, than simply just punching in 4 or 5 numbers. So for this presentation, I used electricity and gas prices from my home residential bill. Understanding commercial and industrial pricing will be a bit different. Why did I put my home information here is because, well, I have that, and I think all of us have that without having to run out right away and ask somebody for the information. So I used the delivered cost. Okay, this is really interesting. I don't know if you guys ever spend time looking at your bills or not, but I used the delivered cost, meaning energy cost and distribution cost, only leaving the GST out. So having said this, my residential electricity is not exactly 6.8 cents per kilowatt hour. It's closer to 15.7 cents per kilowatt hour. And on the gas side, it's a little bit more than 250 per gigajoule. When I did my math based on my 23 gigajoules, in this cold month, I realized I was closer to $9 delivered to my house, including carbon tax, of course, which is a big conversation topic. I think it's getting to this. So the calculator is showing us, values based on this information. It's the reason why I say it's complicated, because sometimes when you're designing a site, your local utility might, if you're doing a new site, the local utility might not even want to tell you what your delivery charges are until you sign a contract, and that's kind of complicated to do any studies on. But also, big commercial clients and industrial clients, they negotiate rates that maybe us as residential clients don't even see possible. So just keep that in mind. This is really for illustration purposes. Again, you could run your own house on here. Just think you might need 2,000 kilowatts instead of only 1 kilowatt, of course. But what this is saying, I put in a couple of pictures here, and it's really small on the screen right in front of me. So look to my bigger screen here. But basically, it splits it up kind of electricity between the just electric utility and the boiler on the left graph, and between the CHP calculation here, with basically saying, hey, I still need to get a little bit of a boiler here for some of the high demand. I'm going to run genset most of the time. I have some maintenance in here. Actually, I think the top is the maintenance and the bottom is my additional heat source of boiler. But what Jim is saying, rather than just calculating here based on dollars and annual savings and everything else, the hot topics today are CO2 reduction, how many cars off the road we moved off, and things as such. We can come back to the calculator and the questions as well. And I think I'm probably going to need Jim to help me a little more with the calculator. But from Caterpillar, I want to cover basically our generator set sizing. We have a chart here right now. It's showing Caterpillar reciprocating engine line. I say reciprocating engine line because Caterpillar also has solar turbines for, maybe from 4 megs on or from 6 megs on. But basically, we have product from about 200 kilowatts all the way to 10 megawatts. Majority what we're doing today here is maybe about 1.5 meg to 2.5 meg or multiples of. But a really, really big hot topic I think might become that you guys see more of and that we might see more of is about 400 kilowatt size, because that's the rec center size. And all the rec centers have swimming pools, and all the swimming pools need a lot of heat. On this next slide, I just want to talk a little bit more about these reciprocating engines. So to give you an idea, obviously, and you probably guys know this, it's a 4-cycle piston engine. They're more efficient when compared to turbines. Reciprocating engines are capable of low load operation with faster start times. So even if you want to just make electricity, that's where they come in handy. You know, yes, we are capable of low load operation, and we can handle so many hours of low load operation. But after low load operation, we're still going to ask you to do basically recovery operation, where we load the genset in steps to the rating to ensure that, you know, there is no whatever carbon buildup and so on. So here is an example, and I put a really big picture of it because I think engine is that mega sized as well. But here's an example of our largest Caterpillar, G20 CM34. On these large engines, we measure displacement and power output per cylinder. This one is 38 liters per cylinder, 500 kilowatts per cylinder, 20 cylinders with a total output of 9.75 electrical megawatts. Kind of flagship engine a little bit because it has a really high electrical efficiency of up to 48.9%. So that means we're just going to get a little less heat on it than maybe on of the smaller end, right? It doesn't mean we're going to cross into, you know, over 100% efficiency. It just means electrically it's really, really got high efficiency. It is capable of many starts, about 3 starts per day, 1,000 starts per year. So that's one of the reasons why it's great for peaking application, as well as combined heat and power. So to give you an idea, we are supplying one of these engines to a site where they're going to actually have Caterpillar turbines as well. And they're going to use turbines for CHP application because they need steam. It's an industrial site, but they still wanted a reciprocating style engine because they recognize the high electrical efficiency that it's going to bring to the table as well. Okay, so from Finning and Caterpillar here, I'm not sure what happened to my notes, where they go. I guess here they are. On this particular unit, from Finning and Caterpillar, we offer containerized solutions, including all the equipment needed. So again, similar to the site we've seen for Edmonton International Airport. Here, the equipment obviously is a generator set, heat exchangers on coolant circuit, heat exchanger on exhaust, muffler and exhaust stack, emission after treatment when needed, heat dump radiators, fresh oil tanks with oil makeup units, waste oil tanks, switchgear, custom PLC controls. So Finning Caterpillar is very well versed in providing custom PLC controls for setting up based on heat demand, based on electrical demand, just strictly to satisfy the site needs. So this one particular packaging, this particular picture is showing packaging within a container. So this is basically modified shipping containers. I think often they're a lot wider than what you see standard container on a train. But better yet, a walk-in style enclosure, as shown earlier for Edmonton International Airport, might be a better choice, just because we deal in cold climates. Again, we have to touch these engines often for maintenance. We want to be able to have good access. And, you know, a lot of times these sites, they get purchased with service agreements. And, you know, there's performance guarantees and everything else. And it's a lot easier to guarantee and commercially close all that contract when you know your technician doesn't have to be outside in -20 or -30 doing major rebuilds or even minor service events. So just keep that in mind, be aware of the installation, and even, you know, a little higher capital X early on might, over the long run of the unit, might provide savings. So again, turnkey solution for containerized site or again, a walk-in style. So here's an example of containerized solution with site-specific informations listed. You know, good gas and good gas pressure is what we need. And by good gas, I mean, you know, pipeline quality gas always helps a little bit better than if it's digester gas or what we've seen at, you know, wastewater stations. Then we got to make sure the engines can handle that kind of gas. So gas sample becomes really important. Altitude and ambient temperature. So there's going to be items that we got to make sure we figure out for that. You know, we might see some D rates based on that. Sound requirement at site. So it's best to be aware of site space, as some city noise bylaws are impossible to meet if product is to be installed close to property line. And I say impossible because I see guidelines for City of Edmonton and City of Calgary. And if you're at the property line, you can't meet those requirements. But again, say you're doing, you know, a wastewater station, or say you're doing a rec center. Usually there is a lot of field and a lot of yard around those kind of installations. This particular site here had extra space for future SCR. They had some site-specific temperature requirements that we had to chase. In this case, generator set net rating was about 2.4 electrical megawatts from a Caterpillar G3520H, so high efficiency generator set. And as we say, we have a special note here for special safety focus, separate electrical control room, easy access doors, fire safety devices, gas leak alarms, and spill containment floor. And I think, Chris, I think you're next here, actually. I think maybe I came to one of my final slides for now. Are you with us there, Chris?
Yeah. Hey, sorry, everybody. Okay. I actually had to jump off and jump back onto my phone because my computer decided to freeze on me at an ideal time.
Earlier, I'll flip your slides if you want.
Yeah, if you don't mind.
You want to control or?
I'm on my phone. I would, yeah, you can just slide through it. I don't even know how to do that on my phone. So bear with me. It's a little difficult to see, but I think I memorized them. So we'll just continue through here.
Okay.
So hello, everybody. My name is Chris Sherman, Project Development Manager at Finning Power Systems. Been with the company for going on 12 years now. Electrical engineer by discipline. Started off in the engineering department, doing some electrical design, PLC and HMI programming, as well as generator parallel control setup and site field testing. So I've had a lot of fun, hands-on fun, and eventually found my way into the technical sales side. I am based here in Vancouver with a frozen laptop.
Well, you could be in Edmonton with a frozen laptop.
The connection on the phone seems to be pretty good. So I'm the anchor of this presentation, and we're just going to talk about a little bit of hybrid power generation and tying it into the CHP presentation that my colleagues here did a great job doing. So starting from the bottom of this list is, you know, one of the key takeaways of this slide is power on demand. You know, you guys talked about resiliency earlier on. So when we're looking at adding renewables, you want to really focus on that resiliency, and that base power is your CHP system, power on demand. Whereas with renewables, everybody knows that they are very dependent, weather dependent, and it is recommended to have some kind of power storage on site where you can use that energy whenever you want to use that energy. And that's usually at peak times or high utility rate times. Moving up the list here, I probably should have reverse the list, but that's okay. And you want to also look at the emissions, because this is where you come into the optimization. So obviously the emissions is high in the CHP, but it's your resiliency emissions and low on the renewables, which is pretty obvious. And then as well as cost of power. Cost of power is high in the CHP, but when the renewables are installed and they're working, cost of power is low. So the thing to do with all these components is optimization. And Caterpillar can help do that depending on what sources you have at site by putting that controller piece there that leverages the lowest cost of energy available, but also has the resiliency of a reciprocating engine for a CHP unit. And so you can go to the next slide. So just to end things off here, we're just going to do a quick example of one of these hybrid sites. Now, unfortunately, it's not a CHP application, but it is a remote site running diesel power generation. And this site is a little hard to read for me right now, but off the top of the list, it was too far away from the utility. It was cost prohibitive to run the utility line in there. Site average load is around 300 kilowatt with a peak of 500 kilowatt. And this was run by 3 C15 Caterpillar diesel gensets. And I think, can't see that fuel consumption. I think it was 250,000 liters per year or gallons per year.
Yeah.
Thanks. And it was around 11,000 runtime hours for all 3 units. So it was a very good case for adding renewables and doing this hybrid system. They've installed 2 250 kilowatt solar arrays with just a little bit of energy storage, not a whole lot, to prop up the system to add that efficiency and use the energy when it was critical. That was a site aerial overview of it. And this is just the simple block diagram of the site. And again, you know, focus on optimization and resiliency is having that master microgrid controller tie everything together. And this is the brains of the system that makes sure that first off, you have that resiliency. So you have the diesel backup there, but also you want to leverage your PV and your energy storage as much as possible, because that is your lowest cost source at the time, as long as it's there. This slide, I felt it was necessary to show everybody. For a remote site, it's very important to recognize that the PV inverters cannot be on the grid just by themselves. If the energy storage was not at site, you would always have to run at least one diesel genset, because the PV inverters are not grid forming. You need something there to actually regulate the voltage and frequency and set that. And in this example, we were able to shut off all 3 of the diesel generators because that little bit of battery storage at site. In this diagram, you can see the flow of energy being created in the PV in the middle there, flowing 100% to the load, and also doing a little bit of charge on the batteries. However, if you look very closely at the batteries, you can see that there's a large kVAR reaction coming from the batteries, because it is setting the power factor for all the electrical people on the call. So it is very important to have another source on there when you're a remote site, such as batteries, or you would be running that diesel generator most likely at a low load. You can go to the next slide now, Sid. This is a somewhat messy slide, but it paints a very good picture of what happens at a remote site. And again, this would be the same as utility, but it shows the importance of the energy storage at site. So the yellow line is your site load, and this is at the Caterpillar Tanaha Proving Grounds. So this is a snapshot from a single day, and it shows the green bell curve is your solar power generation going up. And then as that's going up, the diesel power generation, which is your blue, starts to conversely go down, and eventually it will shut off, and that's that solid blue line at the bottom of the screen there. The white blips are the energy storage discharging whenever there's a cloudy period, and that PV solar power generation dips as well. So that makes up the power difference, and also keeps your diesel generators offline. So without that energy storage there, you would be running at least one generator for grid forming, as well as to take on those cloudy periods. So having a little bit of energy storage saves all that money from shutting off the diesel generators. And another important aspect of this grid is you can see at the very top, there is a little bit of the bell curve that gets chopped off, that white bit at the very top, Sid, and that's PV curtailment. So at that point in time, the PV can actually generate more power than what's needed. That means that the load isn't calling for it and the batteries are fully charged. So the master microgrid controller dials back the PV power generation at that time, just so there's not excess power on the bus at that point. And then at the end of the day, the batteries are fully discharged. As that sun starts to go down, your diesel generators all kick online. charge up the batteries, and make up the difference between the curve of where the power generation starts to go down. So that's a very clear snapshot of what happens on a typical day in a hybrid system. And then finally, adding this system at the Tucson Proving Ground, they were able to achieve 33% fuel cost reduction, which is quite significant for what they've added. They've reduced the generator maintenance by 25%. And I think the return IRR was 15%. And that's based on, I think, around $3 per gallon USD. Opening up the group for questions now.
Yeah. Don't be shy, guys. We can answer any questions, or if you have any insight.
Yeah, I have a question.
Mm-hmm. Yes.
Bruce Payson from DGH Engineering. When the microgrid controller powers down the photovoltaics, does that need to be configured, or is that basically out of the box functionality?
Right. So it is out of the box, assuming that the inverters, either existing or that get put into the site, have the ability to take that command, because the master microcontroller will send that command through communications to that specific PV inverter or inverters and tell them to dial back. So as long as they have the smarts for PV curtailment, which most of them do, they will react to the MMC.
Well, there you have it. We did a presentation on combined heat and power, and we got a question about a microcontroller.
Yeah. Richard here, I've got a question for you. You mentioned earlier in one of the beginning slides about generators being used more so when you have catastrophic events. I know, well, I believe at the Slave Lake fire or something, the first thing they did was turn the natural gas supply off as well. Is that normal, or would they try and keep the natural gas supply on even though there's a fire? Or is it just that area where the whole place was being burnt up?
So this is actually a great question, and I'm glad you asked, because obviously different site, and I'm trying to go a little bit back, but different events will cause for different utilities to be shut off, right? And I think in that case the whole city was burning. If we were in Vancouver, where Chris is, earthquakes, right? So again, we can see gas shut off. What Jim was saying about Hurricane Katrina, all the diesel gensets quit after a day, but all the natural gas ones stayed running. I was talking to the guys in Edmonton here at the Imperial Oil Refinery when the tornado went through Edmonton in '87. Their diesel generators had stopped working a day later because they ran out of fuel inside their own yard in a refinery. They couldn't get fuel to themselves, right? So this is I don't know what the answer is, Richard, because it looks like different events will cause different need, but it's a great debate topic, right? In buildings now, I think we have to have designated gas lines for gas generator sets, no matter what. So that kind of helps a little bit. But I don't know if we have an answer. Jim, do you want to add anything?
Yeah, if you consider the at-risk sources of power, I can't specifically answer Richard's question, because obviously if the place is burning to the ground, you may want to turn the gas off. But if you look at natural disasters, the at-risk energy sources for CHP, we list earthquakes as at a partial risk. The rest of it, if you stack it up against everything else, then no, it's a pretty low risk installation. I wish I could say definitely, Richard, but I can't. Yeah,
so it's basically look at the installation and evaluate the risks associated with it, that for that specific project then.
I mean, if you think about gas codes across municipalities, Richard, I think over the last few years that's kind of changed, hasn't it? I mean, there used to be a code requirement that fuel gas was actually turned off, but that's not the case anymore, as far as I'm aware.
So, yeah, so Jim, and as far as codes go, I think they make the consulting engineer or design engineer responsible, which puts a big burden, on people like Richard. What's the right path to take? From the other point of view, just to add something, the combined heat and power units don't replace emergency generator sets. They're not meant to replace that because a lot of them are built for high efficiency. And Jim, you can maybe comment on this as well, but a lot of them are built for high efficiency. They're not to say they're not going to run in island mode, they can, but you have to really understand your loads and you have to really understand the blocks of loads in what you're going to put on a high efficiency unit. Right, Jim?
Yeah, so I mean, anybody with experience in power generation with natural gas knows that high efficiency engines cannot take block loads. So if we think about that, well, we'll call it by name, Edmonton Lab Hub. The base design on that was for an emergency gas genset that was set up to take the swings. The CHP would essentially base load against the nat gas genset, and the standby genset would take the swings. Yes, but if you have a fairly flat load profile, I think there was a video I actually watched today. There's some hospital over in, I think it's New Jersey, and they do use the CHP genset to ride through and do not sacrifice any of their power at all. They can keep running 100%. Does that explain that?
Yeah, that's good.
Oh.
Thank you.
Dinner's arrived.
Just in time.
I got a question. This is Tachi Murthy. Can you hear me?
Yes, we can.
A couple of questions actually. You had efficiency of 48% or something on a reciprocating machine.
That was on our flagship unit, yes.
Well, that seems to be a bit high for a reciprocating machine. Is it gasoline powered or what was?
So that was
The
only
one,
for that was only for that 10 megawatt unit. Usually
Okay.
they're about 43.
Well, the thermodynamics says the highest efficiency you can get on a reciprocating machine is about 20% or something. Maybe I'm a bit out of date on what has improved so far from the time I learned thermodynamics. I'd like to see how the calculation was made. We can leave that alone. I can research on that. And another one, you said the gas pressure inlet was 3 to 7 psig. Is that correct?
For us, for our gas train, yes.
Oh, it seems very low. So reduce the pressure from wherever you're getting your gas pressure to that low.
Well,
I could maybe take that, Sid.
Go ahead.
Yeah, so most of all of Caterpillar's natural gas gensets are low pressure gensets, which obviously does help. It's not a high pressure system like some others that make it a classified building. With this, we can actually treat the genset like a standard appliance. There is a final regulator on the genset, which actually makes it a zero pressure regulator, but incoming to the gas train pressure is 3 to 7 psi across most of Caterpillar gen sets.
Okay, I have to take your word for that.
So,
Thanks.
I think we have a spec sheet today to show this as well somewhere. It doesn't have to be just our word.
No, well, no, I don't know. The normal gas, anything comes on the line is much higher than 7 psi.
We would need you to drop it for us.
yeah, so typically we can add additional things. So if you're talking about putting a gen set inside an enclosure, to make it a general purpose building needs to be under 66 psi.
Mhm.
So we typically see 50 psi to skid edge. We will then take that 50 psi, add an additional regulator to drop it to 7 psi to the gas train, and then from the gas train to final regulation at the gen set. Does that make sense?
Yeah, good. Anyhow, it's a great presentation. Thank you very much.
Thank you.
Anybody wants any follow-ups or any clarification on anything? I do realize we were hoping to have a bit more time for questions, but we talked too much.
I see Leo has got his hand up. So Leo, ask a question quick.
Yeah. You mentioned emission treatment. What are you using for the treatment? I assume you're reducing SOx or NOx or NOx anyway.
So typically, most of the all the gen sets that we have meet current emission standards across Western Canada. Some places you're going to have to add additional after treatment. So we'll typically meet site requirements, whether that's carbon monoxide, nitrous oxide, whatever. I mean, if you look to Ontario, they have you typically have to meet tier 4. We can do that. If we're given the site requirements, we can meet it.
And what process do you use for that treatment?
On a lean burn natural gas gen set, you only have one choice, and that's a wet urea system.
Okay.
So it's a dosing system, and that's to do with the excess oxygen in the exhaust stream. Because lean burn natural gas gen set, highly efficient. We actually have excess oxygen mixed with the fuel. So what that means is coming under the exhaust stack, you have oxygen coming out the exhaust stack. Anytime it's above 4%, you cannot use a non-selective catalyst. You have to use a wet urea system.
Thank you.
No problem. Oh, carbon monoxide and oxycat as well. That's in addition to that.
And any other questions, anybody? Hearing nothing for a second, could I ask a couple? So have you looked at the overall, you're sort of talking about CO2 and the reduction in CO2 in the operating side, and I understand that part, but have you included the CO2 that's embedded in the materials that are used in the various options that there are? Because some materials create a huge amount of CO2 to produce them, like steel, for example. So when you show your CO2 relative values for the different operating systems, what happens if you look at life cycle CO2 costs?
Oh, sorry, didn't quite understand the question. If we look at greenhouse application, that's CO2 enrichment, which we obviously use.
I think Jim, sorry, I think so. If I understand the question, you're talking about the CO2 it takes to actually manufacture the generator.
Exactly. So you've got various options in generators, and they each have different amounts of CO2 to build them.
Mm-hmm.
Do you take that into account when you produce your CO2 numbers?
Right. So the overall carbon footprint. No, Caterpillar, I don't believe publishes those. I believe that would be a fairly hard number to come by, seeing how thousands of parts from all over the world go into the Caterpillar generator. But I do understand the question. It's just like how you would look at a solar panel or a wind turbine and call that green. But what did it take? What's the carbon footprint to manufacture those components and get it to where it's going? I'm not aware of those numbers. I think it's a good question. Maybe we can ask the factory to see if they have an idea of that, and we can get back to you.
Yeah, that's no problem. I have a second question, if I may. You talked at one point about releasing excess heat to the atmosphere because, especially in the summer, has there been any thought given to producing or using that heat to heat up, say, a huge tank of water, which you slowly heat up over the summer and then you use for warming a building in the winter?
Yeah, so basically thermal storage, right?
Yeah, thermal storage, yeah.
I think, I think the tank would have to be very, very large. I'm not an expert on that. I imagine it would be possible, but it may end up being a really large tank.
Yeah, my understanding is they're pretty large tanks, but they're a way of, as you say, of heat storage. So yeah, I just wondered whether it was an option that had been given any consideration.
Yeah, when we look at even a smaller scale, it's a large tank to do it just overnight over day for overnight, and I can't even imagine how big it would be to do it for multiple days or a month.
Yeah. Okay.
Could I just,
Anybody else got questions?
could I just touch on that? Just want to clarify something, that the question specifically asked about thought being given to store water over time. Typically, that would be taken care of on the process side. We're more concerned about delivering that heat to the process, and the customer engineer designs how they use that heat, how they dispatch that heat. Does that make sense?
Yep, that's good. Thanks. Yeah, no, that's a good point. Anybody else got questions? Let me just see what's in chat. We've just got great presentation. So perhaps in closing, I could reiterate that. Thank you guys very, very much. That was very informative, very helpful, clarified an awful lot of things in terms of CPH, especially for me. We will be making a donation to Operation Eyesight in your name, so to thank you very much for that. And we'll give you the details of that when we've got some information from Operation Eyesight. So somebody in the developing world will get better eyes on your behalf. So thank you very much indeed.
Well, that's cool. Thank you for sharing that.
Absolutely, thank you.
Yes, thank you.
Folks. Good night, everybody.
Good night. Thank you very much.
Everybody.
Thanks.
Bye now.
Good night.
Good night.